All right. Hi, everybody. I'm glad that you are all here. And what I'm going to do in this video is try to efficiently solve problems from this homework assignment for you. I do want to ask you, if you're watching this on YouTube, it's not a bad idea to hit that pause button and think for yourself, what would I do next? And then go ahead and turn on the play and just see how it lines up with what I'm doing. That way you give yourself the chance to really make sure you're mastering it. It's one thing to listen to me explain it, and to understand that is great. But then the next level is to say, okay, I could do this for myself. So if it helps you to challenge yourself in that way, I definitely encourage you to pause the video. I'm going to do a number of the problems from section 4.5 and 4.6 that are on the latest homework assignment. And I'm going to start with number 3, which is the very first problem on the assignment. And it is going to ask whether the set of vectors that I'll write down in a moment is Li or Ld. So at this moment, we're not worrying about spanning set or basis or anything like that. We're just testing whether the vectors are Li or Ld. And if they are Ld, we're going to try to find the linear dependency. Okay, so let's start. On number 3, the set of vectors that they give us consists of the vector 2, -1, and then 3, 2, and then the third vector is 0, 1. Okay, now actually, we already know the answer to whether these vectors are Li or Ld before we even take a breath, because the number of vectors in this set is 3, and the vector space that you can tell what vector space this is referring to just by looking at how the vectors look. They look like vectors with 2 slots. That's R2, and we know that the dimension of R2 is only 2. So this is the scenario where you were given more vectors than what the dimension is for that vector space. Admittedly, in section 4.5, we don't really know what the dimension means yet, but we might as well take advantage of our knowledge of that. So we know that there's too many vectors here. It's basically what we already know. And so I'm already, even before I've done any work at all, I'm already looking at this as being LD. Okay? But in order to find the linear dependency, we are going to have to work a little bit more. Remember that the normal way of proceeding here is to lay out these vectors into the columns of a matrix. So the first column would be 2 and -1. The second column would be 3 and 2. And the third column would be 0 and 1. And if I'm testing for Li or Ld, I would augment that with zeros. Okay? My constants are C1, C2, and C3. And those are really what we are trying to find here. Okay, so we do have to do an ERO or two on this problem. I'm going to do those fairly quickly, and you can do them quickly on your submissions as well. I would probably move the second row to the first row, but I would at the same time throw a minus sign through the entire equation. And then the first row just needs to be moved down to the second row. And I've got myself a pivot here in that first entry right at the top of the matrix. Now I'm going to take that first row and recopy it. And I just need to get a 0 below that pivot. That's my usual routine. And for that, I have to take -2 times the first row and add that to the second row. -2 times the first row added to the second row. And it's going to look something like this. And I'm being a little sloppy again. I'm allowing 7 to be a pivot here. The positions of the pivots is really what matters. And what you can see is that there is a free variable here, which is C3. And see, we already knew that that would happen because this matrix is a wide, stretched out matrix, which just means that you have more columns than rows. And so you have to have an unpivoted column somehow. You kind of know that even going into it. You know that that's going to happen. So and so we just have to allow C3 to be a free variable. I'll call it T, like I so often do. And from the second row of the equation, 7 times C2 plus 2 times C3 is supposed to be adding up to 0. And so I can solve that for C2. C2 is going to be -2/7 of t. All right? And then I'm going to go back to the first equation, C1 minus 2C2 minus C3 equals 0. And I'm going to solve for C1 now. Okay, I'm going to solve this one for C1. So what is that going to give me? If I solve for C1, it's going to be equal to 2C2 plus C3. So 2 times C2 plus C3. So that's -4/7 of t plus t. And so that adds up to 3/7 of t, if I'm not making any mistakes, hopefully. Great. And if you remember, when you're trying to find a linear dependency, once you've set this up like this, the main thing you need to do now is choose a value for t. And if you recall from the lecture, there is only one value of t that you really need to avoid, and that is 0. We cannot let t be 0. But we can choose any other number. I almost always just choose t to be 1, because there's really no reason not to. If I choose t to be 1, then I'm going to get values for C1 and C2 and C3 very easily, right? So C1 is 3/7, C2 is -2/7, and C3 is 1. So that's just plugging in t equals 1. And the last thing I would probably do then is actually write the linear dependency down. So that is just C1 times V1 plus C2 times V2 plus C3 times V3 adding up to 0. So the way that's going to look on paper is 3/7 of 2 comma -1 minus 2/7 of 3 comma 2 plus 1 times 0, 1. And we already know that that is supposed to cancel out to the 0 vector. Okay, so what you have here, this is what is called a linear dependency. And you can check it. You can do the math on the left side and you'll see that everything cancels out. And so you do end up getting 0, 0. We've managed to get these 3 original vectors to cancel out in a linear combination in an interesting way without choosing all the constants to be 0. They have canceled out. So that is a good example. By the way, if you had, let's say you are allergic to fractions, you don't like fractions, no problem. You could have just chosen t to be equal to 7. And then what would have happened if t was 7 is you'd get C1 to be 3, C2 to be -2, and C3 to be 7. And that would literally just be multiplying this box through by 7. It's still a linear dependency, and it's still valid. I'll just remind everybody again, feel free to pause this video if you need to review that last example. You can spend as much time looking at it as you want to. I'm going to move on, though, to another problem. We're doing the same thing on problem number 9. A set of vectors has been given to us, and we're being asked, are those vectors Li or Ld? And if they're Ld, we're supposed to find this linear dependency among them. So by now, I hope everybody's kind of getting in the drill of how this works. We just have to lay these vectors into the columns of a matrix to start off our solution. So I'll do that here. The first column has the first vector in it. The second column will have the second vector in it. And the third column will have the third vector in it. And I'm augmenting this right now with zeros. Okay, so it'll look something like this. I've got a pivot in that upper left corner looking pretty good already. So that's a good sign. And the main thing that we need to accomplish first is we need to get zeros below that pivot. Okay, so I'm going to start by getting zeros below that pivot. So we'll leave the first row the same. And if I add the first row to the second row, I'll get 0 and 1 and 0 and 0. And if I add -2 times the first row to the third row, I'll get 0 and -3 and 3 and 0. And if I add -3 times the first row to the third row, I'll get 0 -7, 4, and 0, I think. Okay? And I'll go ahead and circle a pivot here in the second column as well. It's gonna look something like that. Next thing I'm gonna do is I'm going to leave the first two rows the same. So I'm starting another step here. I'm going to leave the first two rows the same, but I'm gonna take 3 times the second row and add it to the third row. So that would become a 0, a 0, a 3, and a 0. And actually, that 3 will end up being a pivot position. I actually don't need to go any further. The bottom row, of course, isn't really in the right form quite yet. However, I'll just remind you that I already see that every column on the left of my bar has a pivot. There are no free variables here. And when you have no free variables, that means that your vectors are Li. And if your vectors are Li, then there's nothing else for you to do. They're not asking you to do anything further. You can just state that the vectors are Li and you're good to go. So that's all there is to this problem. All right. All right, everyone, I'm moving on. The next problem I'm going to go over is problem 29 in section 4.5. In this case, we're going to work with the universe of 2x2 matrices, and they gave us 3 2x2 matrices here in this set S. Now, whether these vectors are Li or Ld, I don't know just by looking at them. If we do our usual analysis, we would say, well, there's 3 vectors here, so K is 3. And if we look at the dimension of our vector space, the dimension of M2 of R is 4. So remember that when K is less than the dimension of V, what we learned is that those vectors might be Li. We don't know if they're Li yet until we go further. What the question is asking is, in case they maybe are not Li, they want us to determine a set of vectors that is Li that would have the same exact span as these 3 vectors do. Now, what I mean by that, remember, guys, if you have any set of vectors, they always span something. They always span whatever they span, meaning if I take all possible linear combinations of these 3 matrices, I'll be able to create a whole truckload of other matrices, and that becomes a subspace. Whenever you take the span of any vectors, you're getting a subspace of M2 of R. By the way, that subspace will not be the entire M2 of R, because in order to span all of M2 of R, you would need 4 matrices, because the dimension is 4. And so I'm not expecting that these 3 vectors would span all of M2 of R, but they are capable, through the use of linear combinations, to create a subspace that create a subspace within M2 of R, okay? And we're looking for a set of matrices that could get that job done, but which is Li. And I don't know if these are Li yet. So you know what I'm gonna do? I'm gonna first try to just figure out, are these Li or Ld? Same thing we were doing in the last example. So again, I'm gonna take that first vector and lay it into the first column. 1, 2, 3, 4. And then I'm gonna take my second vector and do the same thing in the second column. So -1, 2, 5, 7. And then I'm gonna do the same thing in the third column. 3, 2, 1, and 1. And again, I'm focusing on the linear independence question. For that, I always attach a column of zeros. And I'm going to try to see whether my constants must be all 0 or not. I'll circle this pivot in the upper left corner. That should help me get started on getting this thing into a row echelon form. Okay, so this is the setup. Remember, the answer to everything in Math 250B, how do you do everything in Math 250B? Put it in a matrix. And in this case, you just have to do it correctly. It goes column by column, right? So those vectors go into the columns. I'm going to go ahead and help you through these EROs a little bit, so you can kind of check your work as you're going along. But again, feel free to pause the video and try it for yourself first, just to see if you're kind of getting on top of this. And then you can always start playing the video and check your work. I'm gonna take -2 times the first row and add it to the second row in order to get a 0 below that pivot. -2 times the first row added to the second row gives me 0, 4, -4, and 0. Then I'm going to take -3 times the first row and add it to the third row. That puts a 0 in the first column again. And now on the second row, I'll have 8, on the third row, I'll have 8, -8, and 0. So that is my third row. And finally, I'm going to take -4 times the first row and add it to the bottom row. And when I do that, I'm going to get 0, 11, -11, and 0. Now, what you might notice already is that the third and fourth rows just look like multiples of the second row. So I can go ahead and circle this pivot here around that 4, that's fine. But if I think about it, the third and fourth rows are actually going to get zeroed out, okay? Let's just go ahead and take a look at how that shakes out on paper here. So I'll recopy the first row, I'll recopy the second row, and I will zero out the third row, and I will zero out the last row. So this is essentially what happens. Now, what you notice here, guys, is that the third column does not have a pivot. That actually tells me that these vectors are LD, because as a set, they are LD. By the way, we don't talk about one vector being Li and another vector being LD. It doesn't work on a vector by vector basis. It's the whole set, right? This whole collection right here, this whole collection is LD. It is LD. Why again? Again, the reason is because C3, the third constant, would be a free variable. And when you have free variables, the vectors are LD. So that means we're actually going to have to do something here, because this problem says determine a linearly independent set of vectors. Well, these are not linearly independent, okay? But what we can do, this problem is so much easier than you might think, because what we can do to create a linearly independent set would be to simply imagine if this column was not here. Just imagine it wasn't there, the matrix got narrower here. If that column wasn't there, guys, then there would be no free variable anymore. And that column not being there, if we kind of trace that through, that just means that this third column doesn't exist anymore. And so we get rid of that vector. So the answer to this problem, guys, what is the final answer to this problem? Find a linearly independent set of vectors. Well, we can take just the first two vectors. This is the answer to number 29. It's literally just taking the first two of the three vectors that they gave us in the first place. Okay, and that creates a linearly independent set of vectors in this case. All right. By the way, you'll notice once I'm down to two vectors, they are not scalar multiples of each other, which is a confirmation that they are Li. So we know that they're Li because there's no free variables within the first two columns. But if you want to see it visually, you can just say, yeah, the second matrix is not a multiple of the first one. And so you can't create a dependency anymore among just these two vectors. If I kept all three of them, there would be a dependency, meaning that this third matrix is expressible in terms of the first two. And we could write that linear dependency, if we really wanted to do that, we would, set up our same thing we did on the last examples. We'd let C3 be a free variable. We would back substitute for C2, which I think would be T in this case. And then we would have to figure out what C1 is, which I think would be -2T, I'm pretty sure. And then as soon as I choose T equal to 1, I have -2 times the first vector, plus the second vector, plus the third vector, canceling out to 0. And that would create a linear dependency. Make sense?
Yes, I do have one question.
Go for it.
So before we zero out 8, -8, 11, and -11, I'm kind of having trouble. I can see why the 8 zeroes out.
Yeah.
But then for the 11, I was kind of like my brain, I was trying to go ahead and I was using the first row to try to
Don't use the first row again. If you add a multiple of the first row to the lower rows, you'll destroy these zeros that are here.
Oh,
So you really need to use, you know, it would have been better if I would have made this pivot into a 1. But you just need to use a negative 11/4 of the second row and add it to the last row.
no.
And that will zero out that bottom row.
Okay.
Yeah. All right, everyone, the next one I'm going to work with you is number 31 from the same section, and it's just the same instructions as the last problem that we just worked on. We are this time, however, going to work with polynomials. So my vector space is P2 of R, and you'll notice that in the set S, they gave us 3 polynomials that are in P2 of R. By the way, notice you don't have to have an x squared in a polynomial in P2 of R. P2 of R is polynomials of degree 2 or less. And this third polynomial is only degree 1. But you do see some x squareds in these other positions. So again, determine a linearly independent set of vectors that spans the same thing that S does. Feel free to pause the video and try it yourself. It works just like the last example that we did. So what we're going to do is start off by laying out our 3 polynomials into the columns of a matrix. We do this every single time, right? So in the first column, I'm going to lay out the polynomial 2 plus x squared. I could write that as 2, 0, 1. So notice I never put the x or the x squared actually into the matrix. It's just the coefficients of the powers of x that go into the matrix itself. And then the second one has coefficients of 4, -2, and 3. And then the last one has coefficients of 1 and 0. And we're going to augment this again with a column of zeros like usual. And I just want to know whether these vectors, I'm starting off asking, are these vectors Li or Ld? And to do that, I'm going to need to do some EROs again. I'm going to move the bottom row up to the top. Okay, and I'm going to leave the second row exactly where it is. I won't change it at all. And I'm going to move the top row all the way down to the bottom. So it's going to look something like that. The next thing I'm going to do is try to get this into a better row echelon form. I need to turn this 2 that's in the lower left corner of the matrix, I need to turn it into a 0. So I'm going to leave the first row the same. And I'm going to leave the second row the same. But I'm going to take -2 times the first row and add that to the last row. And if I do that, I'm going to get 0, -2, 1, and 0. So that's -2 times the first row added to the third row. And guys, you see that the third row is the same as the second row. If you now do another ERO, can we just be really fast about this? If I do another ERO, I'm just going to wipe out that row. It's just going to get zeroed out. Let's just not even write it down again. And take a look at what you have. Once again, you have an unpivoted third column. That means that the original set S up here is LD. It is LD. And how do we create an LI set? Okay, if you watched my previous example, you should know how to do this example. If these vectors are LD the way they are now, then what I need to do is remove the vector that's causing all the trouble. The vector that's causing all the trouble here is the third vector. It's not always going to be the last vector that's causing the trouble, but in these 2 examples that we've just looked at, it's the last vector that we need to throw away. So we throw away that third vector, which is basically like getting rid of that third column. And what you're left with then, guys, is the answer to this problem is literally just these 2 polynomials here. So 2 plus x squared, comma, 4 minus 2x plus 3x squared. Again, very similar to the previous example, but this time with polynomials instead of matrices. But the concept of it and what you're trying to do here is the same in both problems. Take a minute, write that down, make sure you're comfortable with that. We are next going to move to what I think are probably the two hardest problems in this section, which are the theoretical problems about linear independence. So this is a good time to take a quick pause. So guys, unfortunately, one of the things that can happen to us in this chapter when we're taking linear algebra is we can kind of turn into robots. It's like, oh, they're asking us about linear independence. So we turn off our brains, we throw the vectors into the columns of the matrix, we do our EROs, we look at our pivots, and then we just write down an answer. Right? And we can get away with that without really understanding what's going on with the concept. Like you can just kind of turn yourself into a robot that can just do that process and then say, okay, yeah, if there's a free variable, it's LD. If there's no free variable, it's LI. And you'd be right about all of that, and you could definitely answer those questions, but you might not really get what's going on as well as you could, right? And so that's the reason that I have assigned a couple of problems here that are a little more conceptual. I can't really put this problem into a matrix because I don't know what my vectors even look like. Are these matrices? Are they polynomials? Like we don't even know what the universe is here, let alone have values, to plug in. Like how would you fill out the first column? I wouldn't even know because, there's no information about V1 other than it's just some abstract placeholder of a vector. So this is a nice problem to force us to remember what linear independence really means, okay? And this is what I'm going to try to show, guys. If I start with some random handful of vectors that are Li to begin with, and what does that really mean, by the way? That really means there's no linear dependencies between them. The only way to cancel these vectors out in a linear combination would be to put zeros, to cheat basically, and put zeros in front of every single vector, right? So that's what Li means. And what this problem is saying is, if you start off with a random set of vectors that happens to be Li, and you multiply all of those vectors through by a matrix, right? Then the new set of vectors that you get, so you can kind of visualize this. You would have a matrix A, and you're multiplying it by this vector, V1, and you're getting another vector that would be over here on this side. It's kind of in the same universe. So this is a new set of vectors that you've obtained by multiplying the old set of vectors by A. And the issue is, are those new vectors still going to be Li? Well, as long as A is invertible, it's going to be true. And we're going to show that here. But we are not going to show that by writing down a matrix, by throwing stuff into a matrix. I make fun of that a lot, that we always just throw stuff into a matrix, sometimes almost without even thinking about it. But we can't do that here because we don't have information to fill this matrix up with. We don't have enough. It's too abstract. So I am going to focus here, guys, on what it is that I'm trying to show in this problem. I've got some assumptions on the first line, but I'm going to leave that alone for a moment and just try to set up how I would show this linear independence. The way you're going to do it, guys, is, so for my proof, the way you're going to do it is you're going to go back to the definition of linear independence, and the assumption for that is that let's assume that these vectors do already cancel out in a linear combination. So let's assume that C1 times AV1 plus C2 times AV2 and plus ... plus Cn times AVn. Let's assume that that is already equal to the zero vector, okay? And again, feel free to pause this video if you need a little more time to understand the setup, because the setup is really important here, okay? Now, what we're hoping to do is, so let's write down what it is we're going to try to do. We will show that C1 is equal to C2, which is equal to ... which is equal to Cn, which is equal to 0. Like that's how linear independence is set up. This is how we set up linear independence, okay? We have to show that those constants are all 0. Now, from this first equation, which is the only thing we really have on the board so far for our solution in blue, we have to try to take a step forward. And the matrix A is invertible, which means there's an A inverse that we can bring into the solution somehow. And just so happens that we can bring that A inverse to try to cancel the A. If this A was not there, actually, that's a good question. Just imagine in your mind that the A is not there. And it's not here, it's not here, it's not here. What would you then have? You would then have C1 V1 plus C2 V2 plus C3 V3 adding up to 0. Well, the original vectors are already assumed to be Li. The original vectors are Li, which means that if they cancel out somehow in a linear combination, the constants of that linear combination would have to be 0. The only way to get the original set of vectors to cancel out is by cheating, by making every constant equal to 0. And we're trying to show that that same thing is true for this second set of vectors. And I'm setting it up, I'm saying, well, let's suppose that they do cancel out, and then I'm going to show you that those constants are all 0. The trick, really, the main trick to this problem is to just get the capital A to go away, to get it out of there. If we can get it out of there, then we'll be able to use this assumption to finish the argument. Okay, I'm just trying to give you the strategy here. Well, if I want to get this A to go away, I'm going to come down here to write a little bit more. I can, first of all, kind of put the A out in front of everything because there's an A in every single term. I'm just going to kind of factor it out. If I factor that A right out into the front, right, it basically can be factored out like that. Now notice that I didn't switch the order of anything except the constants. The constants can be switched with a matrix, but I would not have been happy for you to put the A on the other side of the V1. That would not make sense because, you know, you can't take a column times a matrix. This size, if this is my V1 and this is my A, that doesn't even make sense. This is n by 1 and this is n by n, and that's just not compatible for even doing the calculation as we learned way back when we studied matrix multiplication. So I don't want you to switch the A. Like if you factored the A out on the right side here, it would be incorrect. It would be incorrect. It has to come out in front. Okay? Now the A is invertible. So we're going to use that to cancel this A right now. So since A is invertible, we can multiply by A inverse. And I'm just going to do that. So I'll have an A inverse times A times, C1 V1 plus C2 V2 plus dot 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 plus Cn Vn. And then on the other side of the equation, we also have to do the same thing. So we have to multiply by A inverse times 0. But I'm sure if I gave you half a second to think about it, you would know that A inverse times 0 is just still 0. Right? So that's perfectly okay to do that. What happens on the left is the A inverse cancels with the A. And look where we are at now, guys. Where we are at is that C1 V1 plus C2 V2 and plus dot 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 up to Cn Vn, that is adding up to the 0 vector now. Okay? The capital A is gone. And the original vectors were Li. What does that mean again? I'm just going to remind you one more time. It just means that anytime a linear combination of those vectors cancels out, like it does here, then the scalars of that linear combination must be 0. And that's exactly what we want to conclude. So let's just write that down and then we're going to be done with this problem. So we're just going to say here that since the set with v1, comma v2, and comma dot 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 up to vn is Li, we conclude that, and the conclusion is exactly the thing that we needed to show, which is that all of the constants are in fact 0. And that, my friends, is the end of this problem. Essentially, when we get to the point where all of the constants must be 0, we know that the vectors that we started with are Li, right? So it's a little bit of an abstract one, but it's a good one to kind of remember the definition of Li. If you need to, look that back up in your notes again, right? So we definitely wrote that down on the board in class. The definition of linear independence it's a slippery definition. And I like to do a couple of examples like this to just really get a little more comfortable with it. Okay, let me pause this for a second. All right, everyone. Now, in this last problem from this section, we're going to do one more theoretical problem. What it's saying is, if I start with two vectors that are Li, and again, it's abstract. I can't put these into a matrix. I don't really know what they would look like. If I start with two vectors that are Li, and I throw a third vector into that set. Now, normally when you do that, you run the risk of introducing linear dependencies, right? The larger your set of vectors is, the more likely that there'll be relationships among them somehow, somewhere, and that they would be LD. So that's a risk. But what this problem is saying is that as long as you throw in a new vector that is not part of the span of what you already have, then the vectors will safely stay Li. Okay, it's conceptually, it would make sense, right? That this is something that needs to be explained. Starting with some linearly independent vectors, if I throw in another vector, there's a risk that those vectors might not be Li anymore. But as long as the new vector that you throw in was outside of the span of those first two vectors initially, then your whole set is Li. Okay, so I'm going to do this one again from the definition of linear independence, and I'm again going to tackle this thing that we're being asked to show, which is that these three vectors are Li. Let's assume that C1 times V1 plus C2 times V2 plus C3 times V3 does in fact add up to 0. Let's assume that one, right? And again, just like on the last example, we will show that C1 is equal to C2, which is equal to C3, which is equal to 0. So it's the usual thing to show linear independence abstractly. I'm not going to put it into a matrix. Instead, I'm going to try to show that the constants of that linear combination must be 0. The only way to cancel out your vectors is by throwing zeros in front of those vectors. Okay, well, this is an interesting problem. I would not expect people who've never seen this kind of thing before to know how to do this without a little bit of help. So that's what I'm here for. I actually really like this problem. What we are going to do is we are going to take a moment and address what would happen if C3 wasn't 0. I'm going to focus on C3. You'll see why in just a second. What would happen if C3 is not 0? In that case, do you agree that I could take my starting assumption here, and if C3 is not 0, do you agree that I could solve that equation for V3? Just move the other terms to the other side and then divide by C3, right? So then we could actually solve for V3. And it would be, let's just write down how it would turn out. it would turn out to be negative of C1 over C3 V1, and then minus C2 over C3 V2. So that's just some algebra. Now, of course, what I'm doing here would be illegal if C3 was 0. You notice we've got it in the denominator of these fractions. It wouldn't make sense to put it there, except that I'm imagining for a moment that C3 is not 0. This equation right here, my friends, is expressing V3 as a combination of V1 and V2. In other words, what it's really saying is that V3 lives in the span of V1 and V2, doesn't it? Which is what we said in the problem. We're going to assume that's not true. So this is, I would just say, violating the assumption. And it's this assumption right here. Right? It would be violating that assumption. Because we are assuming that the vector that we added to our set is not in the span of the first two vectors. Okay, so that means this cannot happen. You must, therefore, there's no way around it. The C3 must be 0. If C3 was not 0, we run into all kinds of contradictions to what they assumed in the problem. Okay, so C3 is equal to 0. Given that new information, if we look at this boxed equation, if C3 is 0, we can kind of just not think about that third term anymore and just reduce it down to C1 times V1 plus C2 times V2, adding up to 0. We can just not bother to write down the C3 V3 part because C3 is 0 anyway. Well, now what do we have, guys? What we have now is a linear combination of only the first two vectors that is canceling out. And we said something in the question about just the first two vectors. The first two vectors by themselves are Li. So anytime the first two vectors are canceling out in a linear combination, it, again, going back to the definition, it must mean that the constants of that linear combination must be 0. We have to cheat to get these vectors to cancel out. Okay, so let's just finish our proof. There's just one more line to go. Since V1 and V2 is Li, since V1 and V2 is Li, we conclude that C1 and C2 are also equal to 0. And putting that together with C3 being 0, and now C1 is 0, and now C2 is 0, we've accomplished our goal. We've accomplished our goal. So all of the constants are 0, and so if we just want to write the final conclusion here, V1, V2, V3 is Li. That is Li. Awesome. That's problem 49. All right, everyone, what I'm going to do now on the rest of this video is look at the problems from section 4.6. There's a good number of them in the assignment that we're looking at right now. And as you're about to see, these tend to go much faster than the ones that we've just looked at before. And in particular, at the beginning of the exercise set, they give you a set of vectors in Rn, and they just ask you whether they form a basis or not. So the very first problem is number 4. And let's just write down what the set is that they gave us on problem number 4. 1, -1, 1 is the first vector. The second vector is 2, 5, -2. And the third vector is 3 and 11 and -5. So these are the vectors that we have. And you can tell what the n is just by how many slots there are in each vector. So you can see that these vectors live in the universe of R3. So these are vectors in the universe of R3. And so the question is, are they a basis for R3? Well, the first thing I would always recommend doing is count how many vectors you have. 3, right? 1, 2, 3. And the dimension of R3 is also 3. So they do match. They do match. Now that doesn't guarantee that they are a basis though. What we have to do is throw them into a matrix. And the usual way, we throw them in column by column here. And of course, it's a square matrix. And one option that I could use is to augment this matrix with 0/number symbols. But there's actually an easier way here. And the easier way to do this is to not even draw that extra column. The easier way is to just say, look, I'm just going to take this 3x3 matrix. And what's something I always know that I can do with a square matrix that always seems to be useful, and that is taking the determinant. So I'm going to take the determinant of this, and I'm just going to use the arrow method since it's only a 3x3. And just use the arrow method, and so the determinant of this matrix, A, if I just use the arrow method, I'm going to get -25, and then +22, and then +6, and then -15, and then -22, and then -10. And we have to calculate that whole thing out and just see what we get. Let's see, -3, add 6, that's 3, -3 is -12, add 22, and we get +10, subtract 10, look at that, we get 0. We do get 0. And of course, we should think of that as being a bad thing. When the determinant is 0, it means the matrix is not invertible. And when the matrix is not invertible, then when we're asking, is it a basis for the vector space? Well, it's a bad thing. That would mean I'm expecting it to be no. And that's the answer. This is not a basis. All right, guys, on this next problem, which is number 9 from section 4.6, we're going to do exactly the same thing that we did on the last problem, except that this time we're working in a universe of polynomials. First thing I always like to do is count how many vectors did they give me. I can see just by looking at the set that there are 3 vectors in that set, so that would be the k value. K is equal to 3. And then if we think about the dimension of P1 of R, hopefully we remember these dimensions. I did suggest that you memorize them. So in the case of P of the polynomials, the dimension always just goes up by 1. So the dimension of P1 of R is just 2. And the minute that you see that, you know that these vectors cannot be Li. And so they can't be a basis. So I don't even have to put this into a matrix, guys. Without even taking a breath, I know that the answer is no. It's just that simple. All right, guys, why don't we just, that was so fast. Why don't we just run that back on another example? Okay, so I'm going to do the same exact thing again. I'm going to determine whether these 3 polynomials here, right, whether they form a basis for P2 of R. Now, in this example, I'll start the same way that I did before. I'm going to count how many vectors are in my list. 1, 2, 3. So K is equal to 3, right? And then I just have to think about the dimension. In this case, we're looking at the dimension of P2 of R. And again, if we remember our dimensions, the way I hope that you are starting to learn them, you would know that that is also 3. So in this case, the values match. And when they match, like they are here, we have to go a step further to test whether they really will be a basis or not. So this involves just setting up this matrix. The first polynomial gets laid out into the first column of this matrix. I'll write it as 1 and 0 and -3. And then the second vector gets laid out into the second column, which would look like 0 and 2 and 5. And then the third one would look like a 1 and a -1 and a 3. So this becomes our matrix. And guys, we just did one very similar to this a few minutes ago. I just have to use the determinant here to test this thing out. So I'll recopy the first two columns and use the arrow method that we hopefully are pretty familiar with by now. So using my arrow method, the first arrow is a 6, the next one is a 0, and so is the next one. And then if I start subtracting the arrows going the other way, I would be subtracting -6, and then I would be subtracting -5, and then I would be subtracting 0. So I did that kind of fast. Feel free to pause the video if you're going a little slower on the arrow method. That's totally fine. But you just get these numbers here that you need to add up, and the only thing you need to know about them is that this does not add up to 0. It does not cancel out to 0. That means that your matrix was invertible, and I'll just remind you that good goes with good. If the matrix is invertible, that's a good thing, and therefore, are they a basis for Pn of R? That's a good thing. It should be a yes. It should be a yes this time. And that's all we have to do, determine whether we have a basis or not. It's either going to be a fast answer because the K doesn't match the dimension, or if it does, like it did here, it's just a little bit more work, which is to just take the determinant, and you'll get your answer every time. All right, fantastic. All right, guys, as if that's not enough, I hope you're not getting nauseous from all these problems that are like almost the same thing, but I want to give you an example in the universe of matrices this time. Suppose that we have m by n matrices, and they gave you the values of m and n here. And then they gave you a set of 5 matrices. I didn't even write down what they are. They are in the book. If you look up this question, you'll see what they are there. But the point of the fact of the matter is, I don't even need to know what they are. Look how fast this is going to be. The number of vectors in my set is 5. And what is the dimension of my universe? So this would be m of 3 by 2 of R. Well, we learned in class that the dimension of m by n matrices is just m times n. So this would be 6. They're not the same numbers, so even without taking a breath, it's already no. I hope that wasn't too boring, and I hope you didn't blink, or you might have missed it. All right, guys, we're going to play this game one more time. All right, just to really make sure that this is totally solid. This time I'm going to work again with m by n matrices. This time m is 2 and n is 3. So these are 2 by 3 matrices. And you can see that this time I actually did write them all out, okay? And the first thing to notice is that the number of matrices that's in this set is what you want to count, right? That's the K value. So in this example, you can see that K is 6. All right? And the dimension of your universe here, so the dimension of the 2 by 3 matrices, well, that's 2 times 3, which is also 6. So on this problem, the numbers match. The numbers match, which means they might be a basis. They might be. If I really wanted to test whether they're a basis or not, I would now have to do the following, and don't write this down yet. Okay, don't write this down yet. The first vector would have to be smeared out into the first column. The second matrix would have to be smeared down into the second column. And you'd keep filling it out like that. And what you would have is a 6 by 6 matrix. Now, the earlier examples in this video, they were all like 3 by 3, they were pretty small. We could just use the arrow method. A 6 by 6 is not totally beyond what we would be capable of, but it sure sounds like a pain. It sounds like a pain to like take a determinant of a 6 by 6 matrix, especially the time I'm recording this is like almost my bedtime. So it's way too big of a matrix to just do the determinant. So I'm wondering if we could hit the pause button on this video and think a little bit about just looking at the vectors. If there's something we notice that just happens to be giving us a clue about whether these vectors are going to be Li and spanning the space or whether they're not. Okay? This is not something that you might notice immediately. You might have to sort of live with this setup for a minute and kind of stare at the vectors. But I promise you that once you see the relationship that I'm thinking of, you're gonna totally know the answer to this question. Again, is it a basis or is it not a basis? So hit that pause button if you want. These 6 vectors, are they Li or Ld, or do they span M2 by 3 of R or not? That's what we really have to figure out. Well, there's actually something to be noticed here, and it's really just pure luck. But if you look at the 5th vector in the list, I'm going to call that V5. If you look at V5, which is 2, 2, 2, 2, 2, 2, it looks almost like the first vector, which was 1, 1, 1, 1, 1, 1. And in fact, if we wanted, we could just notice, again, this is without setting up a matrix at all, we could just simply notice that V5 is 2 times V1. And what you're looking at right here in front of us now on the board, guys, is a linear dependency. It is a dependency. That is bad, right? This is LD. This shows that the vectors are LD, and so they're not holding up the rules of a basis. A basis must be Li, and a basis must span the vector space. And these vectors are for sure LD. So because of that, we can say no just by observing this relationship. If you don't happen to notice that, then your fallback approach is to do the big 6x6 matrix and see if you can figure out whether it's invertible or not. So that would be much more tedious than just kind of observing this at a glance. But it's nice to know that even if you just weren't on your A game and you didn't happen to see this, and you just like, oh, this is 6 random matrices, even in that scenario, you can still get to the answer, right? You just have to work a little bit harder to get there. Okay, so this is not a basis because the first vector and the 5th vector are scalar multiples of each other. Actually, you might remember that in the case when the k matches the dimension, I mentioned in class that the vectors must be both or neither. So there's no middle ground on this one. As soon as the vectors fail to be Li, they actually also fail to be a spanning set. So if somebody asked you a follow-up question, okay, they're not a basis, fair enough, but could they still span M2 by 3 of R? Would they still be a spanning set? The answer is no, because in the case when the k matches the dimension, you don't have any middle ground. It's either fully a basis, which is what both means, it's fully a basis, or else everything goes bad. And in that case, it would be neither. So this is not a spanning set, and it's not Li. Awesome. All right, guys, I think we've practiced that enough. I've got a new problem, kind of a fresh topic here that I'd like to do from the homework. This is problem 20. Again, we're working with the concepts of basis and dimension. And in this case, there's a specific matrix given to us before we even start the problem. And it's this 2 by 2 matrix A right here. And they're asking us for the dimension of the null space. Now, I'm just going to remind you that there is a fancy word for that we did introduce in the class. It's called the nullity of A. Okay? And so they're asking us for the nullity of A in this case. And whenever you're thinking about that, you should almost, as an automatic knee-jerk reaction, you should be thinking about that rank nullity theorem that we've written down in class. This is the easiest theorem in the world to use, but you just have to remember it and kind of know when to pull it out. When you get a question dealing with nullity, it's a good time to just write that back down, okay? Now the n in this formula is just the number of columns in the matrix. You notice that this is a 2 by 2 matrix, so the n is 2 here. And so we have to play these numbers off of each other, they have to add up to 2. The rank is just the number of pivots in this matrix. So I just have to do one ERO here. And you probably can see it already in your head almost. The first row is good to go. I just need to take 2 times the first row, add it to the second row, and it wipes it out completely. And this is your row echelon form. Okay? So this is another one of these problems. If you blink, you're gonna miss it, because I already know that the rank is 1. The question is asking me, what is the nullity? Well, they just have to fill in the box, right? It's a 1. The nullity of A is 1, and the rank nullity theorem gets us there. If they actually wanted us to find the null space, that would take just a minute longer, right? If they actually want you to find the null space here, you don't have to do this for the homework, but just so you are aware, we would have to actually do the usual thing where we set up a free variable for y, I would call it t. And then from that first equation, we would solve for x, which would be negative 3t. And then from there, I could write down my basis for the null space. The basis, if I bust out that t from the 2 slots, if I bust out that t, I would have negative 3 and 1, and that would be your basis. So that confirms that the dimension is only 1, because there's only 1 vector in that set. So this is just finding a basis for the null space if you wanted to do that, even though this problem's not asking for it. All right, I've said more than enough about this problem. All right, guys, we're just going to practice that one more time really quick on problem 21. This one is even faster than the last one. If you look at this matrix, it's already in row echelon form, basically. There is just one pivot. So the rank of this matrix is 1. The question is asking us, what is the dimension of the null space? Well, again, when we add the rank to the nullity, when we add them together, we have to get n. And this matrix has 3 columns, so n is 3. So you can see that the nullity just has to be equal to 2 to make it work out. And that's the answer to 21. All right, guys, I'm back with problem 24 now. This one, based on my past history, does sometimes throw people a little bit off, so I just want to be really careful with this one. We're looking at a subspace of R3. We're going to call it S. And what is it? Well, the subspace is going to be the solutions to this equation right here. And if you want to pause the video for a second and think if this equation looks anything familiar, like you've seen what this kind of equation is, then that might be a good thing to think about. You should have seen lots of these in Calc 3 because we're working in R3. And so this is going to be hopefully a pretty familiar looking equation. We're kind of taking our word for it at the moment that this is a subspace. I can see that it passes the 0 vector check. If I put in 0, 0, 0, it does work. But you know, the closure under addition and scalar multiplication might take a minute of sweat to verify that one. Yeah, but we're going to kind of take that as a given because the question says that it's a given. And the only reason I mention that, guys, is because you can't find a basis and dimension for something that's not a subspace. It wouldn't even make sense. So I really need to be convinced, or at least be told, that S is a subspace before anybody asks us to find a basis or a dimension. Okay, so I'm going to give you 2 ways to think about this. One way, maybe in fact I might even give you 2 full-blown solutions. You're like, I only want 1 solution. But actually 2 solutions is helpful. The first solution is a little bit more of a geometry solution. So I'm going to call this solution number 1. And it gets back to what I was just asking rhetorically for you to think about a minute ago from your Calc 3 class. This equation should remind you of a plane. It looks like the equation of a plane. And if I think about a plane is like a flat piece of paper. And if you thought about like what would be the dimension of something that's flat like that, just a, you know, even just the xy plane is flat, right? Then it should be reasonable that the dimension of S is 2. And this would be since S is a plane. Okay, so we really are appealing to a little bit of our geometry intuition here, like that we know that, you know, lines are 1-dimensional, Planes are two-dimensional. The XYZ three-dimensional space, yeah, that's three-dimensional, all right. So it's kind of makes sense that the dimension is 2. Now, the question asks us to find not only the dimension, but actually a basis. But here's the thing, my friends. If we know what the dimension of it is ahead of time, then the only thing left for us to do is come up with 2 vectors that would form a basis for S. It has to be 2. If I know that the dimension is 2, then I'm looking for 2 vectors. And you know how you can get 2 vectors that are in S? You can literally just eyeball the plane and put in some X, Y, Z values that would work. And so, for example, I could put in the vector 3, 1, 0. 3, 1, 0. Check it out. If x is equal to 3 and y is equal to 1 and z is equal to 0, it is 0. It does work. Now, I need a second vector, and so I can actually just go back to that same process again and just grab some other random vector that I could find. The only thing is, we do want to be careful. The second vector that we pick should not be a multiple of this vector. Because after all, when you have a basis, there should not be any linear dependencies. So like, for example, you could, don't write this down, but you could think, well, I could do 6, 2, 0. And yeah, if you plug in 6 and 2 and 0, it works. It's part of S. But the problem would be that the second vector is now just twice the first vector. These vectors are LD, it's not going to be a basis. Remember, a basis has to be LI and a spanning set. So what I would do instead is find some other XYZ combination that works in this equation without taking a scalar multiple of this one. So, you know, you could just, there's lots of things, right? You could pick 1, 0, -1. That would be an example. So if x was 1 and z was -1 and y was 0, that would work. Okay? Now here's the thing, guys. The dimension of S is 2. The k value that we've written down is 2. That's how many vectors are here. It's the right number, so it's both or neither. In this case, it's both or neither, but guys, these are not scalar multiples of each other, which means they are definitely Li. They are definitely linearly independent. Remember, when you only have 2 vectors, you don't have to go through a whole matrix thing. You can just look at this and say, aha, they're not scalar multiples, so they are Li. And if it's a thumbs up on Li, then guys, it's automatically also thumbs up on spanning of S. It will span S. It's got to be both or neither. I can just look at these 2 vectors and recognize that they are Li, and therefore they must also span the space. So this is one of many correct answers. I invite you to make up your own. Like, we could have done something else. We could have said, I'm going to pick 0, 1, 3. That would have worked, right? And then I could have picked 2, 1, 1 as my second vector, I think. 2, 1, 1 would also have worked. These are also not scalar multiples of each other. And there's 2 of them. So this is another correct answer, okay? So just pick your favorite one and go with it, and there's nothing wrong with doing that. This is the first solution that I wanted to show you. And at the risk of blabbering on too long, I am going to show you a second solution because it's instructive, it's helpful to see another way to think about this problem, and it's completely different. It's a completely different way. It looks a little funny, my friends, but this one equation in this box can be thought of as a null space of a matrix with just one row. It's a matrix with just one row. This is a totally different solution. Notice I didn't use the word null space over here at all. So now I'm thinking null space. I've got my pivot right there, right? So I've got x, y, z. And I can think of, okay, so z is a free variable and y is also a free variable. I like to use r and t a lot for those. And if I now solve for x, well, I can solve for x by, just solving it in the equation. So it would be 3y minus z. So x is equal to 3y minus z, which is just 3r minus t. All right, and so there's your null space. Let's just write down what it is, and then I'm going to bust out the variables on it. So the null space would be the vector 3r minus t, comma r, comma t, such that r and t are real numbers. Okay? And let's just bust out the r and bust out the t. And when we do that, we will get our basis. When I bust out the r, guys, I get a 3, a 1, and a 0. And when I bust out the t, I get a -1 and a 0 and a 1. It's actually almost the same as the first basis that we found over here, except that the second vector is a negative of what we had found before. But there's nothing wrong with that. Again, there's lots of right answers. There's lots of right answers. And this would be the result of busting out the variables and then making your list. Again, it's two-dimensional. It's a plane. When I think of a plane, my geometry intuition is, that's two-dimensional. And so I'm not surprised to see that answer. Okay, so I don't know which way you like better, but this way is, of course, more classical, like going with what we've been learning lately. Null spaces and matrices. This one is a little bit more, okay, we got to be thinking geometry about it. And geometry is not always on the front of my mind when I'm taking a linear algebra class. But yeah, that's it. I'm going to call that good for now. All right, guys, behind me on the board, I've written down the next problem, which is the same kind of problem as the one we did before. It is number 28 in section 4.6. And we're working in the big universe of 2x2 matrices, and we're letting S be the 2x2 upper triangular matrices. So it's all being given to us in words. We're going to have to put some math to those words. But the upper triangular 2x2 matrices is really what the star of the show is here. And we need to figure out a basis and the dimension for that. Okay? So what I would recommend that we do is, first of all, just make sure we know what kind of, vectors these are. These are going to be, 2x2 matrices, but they need to be upper triangular. So that just means there must be a 0 in the lower right corner. So you're probably recognizing what I'm doing right now, which is I'm writing down the general form of a vector in S. And the other numbers in this upper triangular matrix can be anything, and they don't have to have anything to do with each other. So it could just be A, B, and C. Actually, that's the whole thing. That is the form of any element of S, right? So that's the first step, is to just make sure you know what these vectors will look like. Now, we did problems earlier in this theory where we were asked to find a spanning set. And you remember there was a 3-step process. The first step was write down the form. The second step, okay, pause this video if you want to think about it for a second. Okay, because this is something you definitely should have like internalized by the time we get done with chapter 4. If you want to do the second step, after you write down the general form, you should think of those 4 magic words. Bust out the variables. So that's exactly what I'm going to do right here. I bust out the A, and I look at where I have the A. It's just in the first slot in the upper left corner. And then added to that is B times 0, 1, 0, 0, and then plus C, which is multiplied by 0, 0, 0, 1. And so we end up with these 3 matrices. And so then remember that, so this is what I usually call, step B. I don't know if you remember I had 3 steps. Step A was to just write down the form. So that's kind of right here at the beginning. Step B is bust out the variables. And then step C, which is the last step, is where we just make a list. And you don't even have to work very hard at this. You just have to list these vectors like I'm doing right now. Notice that in your list, you do not see the A, the B, or the C. Like the little a, little b, and little c that I wrote down, those go away. Okay? Now, these three steps, they were the steps to get a spanning set for a subspace. This is asking slightly different question. This question is asking for a basis. So I have to remember what's the difference between a spanning set and a basis? Well, a basis is just a spanning set that is also Li. Is also Li. So my only hesitation right now with this spanning set is to make sure that it's Li as well. So I can test that, right? I can test that very easily. I lay my vectors into the columns of a bigger matrix here, right? So 1, 0, 0, 0, and then 0, 1, 0, 0, and then 0, 0, 0, 1. And if I'm checking for Li, I would augment this with zeros. But as you can see, my friends, there are no free variables there. Every column has a pivot, and that's always the telltale sign. I realize that there's a row of zeros, but that row of zeros really doesn't matter in terms of whether there's free variables or not. The free variables is coming from unpivoted columns, and I don't have any of those here. So there's no unpivoted columns. So this set of three matrices is Li. It's Li, and it was already a spanning set, because we learned how to do that in section 4.4. Finding spanning sets. You write down the form of the vector, you bust out the variables, and you make your list. This is your spanning set, but it's more than just a spanning set. It's also Li, and that means that it is a basis. It is a basis. And once you know that that is a basis, guys, you are basically there, because the dimension of anything is just how many vectors are in that basis. And you can count them 1, 2, 3 right here. 3 dimensional. Okay? Our big universe would have been 4-dimensional. M2 of R, we learned that that's 4-dimensional. Within that 4-dimensional space, I have the 3-dimensional subspace S of the upper triangular matrices. I invite you guys to, if you've got some time, try some other variations. What would be a basis and dimension for the symmetric 2x2 matrices? What about for the skew symmetric 2x2 matrices? What about for the lower triangular matrices? I could take this word right here, upper triangular, and replace it with some other word that we've learned and ask the exact same question, right? So it always goes the same process. Write down the form of the vectors, bust out the variables, make your list, and now one last thing is to do this. I guess we could call this an Li check. That's really what's going on over here. An Li check. There's no free variables there, so it is Li, and that means you do have a basis. Okay, I hope that makes sense. I'll leave it at that for now. All right, everyone, we've made it to the last problem. Okay, this is number 32, and they're asking us, this is a different problem. We haven't done one like this yet. Determine a basis for the span of these 4 vectors right here. Now, the first thing to keep in mind is that my big universe on this problem is M2 of R. I can see that these are 2x2 matrices, but the big universe isn't really front and center of what's going on. The main thing is this S, I'll call it S, that we're working with right here. So it is the span of those 4 vectors. Now, because it's a span, I know it's a subspace. Okay, just reviewing, just a chance to review while we do the homework. So it is a subspace, and because it's a subspace, it will have a basis. What I can tell you for sure is that these 4 vectors will span S. Remember, to be a basis, I've got to be a spanning set and Li. Well, these 4 vectors are already halfway there before I even take a breath, because they do span S. Why is that? Well, it's because that's what S is. S is the span of those vectors, right? I don't have to worry about it. I don't know whether they span M2 of R. That's a different question. But do they span S? Absolutely, because S was created as their span. So they are a spanning set, which is half of what is required for a basis. The only thing that is up in the air at this moment would be whether they are Li or not. Linearly independent is the other requirement. Actually, it's not so much up in the air because you never, ever want to spend $1,000 on a zero vector. So I already know that this is a bad guy. We're going to have to do something about that. But let's just kind of go through the motions and see how we would play this out. And at some point, I'm sure that that will come to the surface. I'm going to do an Li check right now, guys. I'm going to do an Li check. And as usual, I lay these vectors into the columns of this matrix. So 1, 3, -1, 2. And then the second column would be 0, 0, 0, 0. The third column would be -1, 4, 1, and 1. And the fourth column would be 5, -6, -5, and 1. And I would augment this with a column of zeros like so. And what we have to do, as usual, is get this matrix into row echelon form. So if you can bear with me one last time doing a few EROs, we will get there, okay? So I'm going to do my little twiddle symbol. The first row is already good to go. I'll just recopy that one. I'm going to take -3 times the first row and add it to the second row. So I'll get 0 and 0 and 7 and -21 and 0. And then I'm going to add the first row to the third row, and I'm going to get 0, 0, 0, 0, 0. Okay. First row and third row. And then I'm going to take -2 times the first row and add that to the bottom row. And I'm going to get 0 and 0 and 3 and -9 and 0. Okay? Feel free to pause the video if I'm going a little fast. I'm trying not to dwell on the EROs too much. But we are now almost there. The only thing left is I'm going to move the all 0 row to the bottom and do a couple other little things. So the first row is going to stay the same. On the second row, I'm literally going to multiply through by 1/7. So I'm going to make that into a 0, a 0, a 1, and a -3. And then the third row was all zeros. And actually, I can make the fourth row also completely zero out because the 1 and the -3 is going to be cancelable with the 3 and the -9. So the bottom row, if I do my EROs, is just going to look like that. And I'm going to circle my pivots. I'm going to circle my pivots. What I can see from this is that there are free variables here. And free variables is bad when we're doing the Li check. You remember, right? So when we have free variables, this is not a good thing. And that would be the second and fourth columns. So if I want to make my vectors to be Li, I have to remove the columns that are creating the free variables. And notice that it's not necessarily always the last columns. In this case, there's actually 2 columns that both need to be removed because there's 2 columns without pivots in them. Now, if I remove those columns, I will then have no free variables. But removing those columns is, in effect, what you're saying is you're going to remove the corresponding vectors that created those columns, right? And so what is your basis? How do you now sort of get to your final basis for S? Well, you just write down the vectors from that list that are still with you, which is just the first one and the third one. Right. It's actually a 2-dimensional subspace inside of the 4-dimensional universe of M2 of R. It's a 2-dimensional subspace. It's very common. I've asked this question before. I'll throw a bunch of vectors here and I'll ask people what the dimension of it is. and they'll try to just count the vectors here and tell me that that's the answer. That's not the answer. There were 4 vectors here. We spent $4,000, but they did not span 4 dimensions. They only span, basically, these 2 vectors were the only things that we needed for our basis. It's actually only 2-dimensional, and we should have only spent, if we were smart, we should have only spent $2,000 to make that basis like so. We've seen this theme a few times. You're going to see it again when you start looking at the midterm review materials. But now that you've seen some examples of it, hopefully it won't throw you off too much in the future. Guys, I know this was a long video, but it was supposed to be more than just going over the homework problems. I wanted to kind of review a lot of the stuff we've done in the last week or two as part of getting these problems done. I think it was pretty fruitful in that sense as well. So thanks for hanging with me out there. I really appreciate it. If you've got more questions, I really hope that you'll stop by my office hours to ask me. I really enjoy this material so much, and I'm always happy to talk more about it and try to give you a hand. Thanks again for tuning in, and I will see you all again soon. Thanks. Bye for now.